we can start. And it is a pleasure for me to introduce our today's speaker, Professor Wu from Tennessee State University. And Professor Wu will tell us about very interesting, very exciting subject about analysis of reaction diffusion, susceptible infected, susceptible epidemic patch model, incorporating movement inside and among patches. Please, you can start your presentation. By the way, just a short question. Usually we try not to interrupt our speakers too much, and we keep our questions for the discussion at the end. But if occasionally there is a short question for understanding, I hope you will not mind if we interrupt you to ask this question.
Oh, sure. Yeah. Feel free to ask me anything. Yeah.
And by the way, it's exactly that. We have already one question. Please, do you have a question? Oh no, it disappeared. Okay, apparently no. It was a raised hand, but then it disappeared. So looks like no questions at the moment. So please, you can start your presentation.
Okay. Thank you. Firstly, I would like to thank the organizers for the kind invitation. It's my great pleasure to talk about my research here. My talk will be based on a recent work joined with my collaborator, Shan Chen. She is in this Harbin Institute of Technology. Okay. All right. Okay, we know that mathematical models have been used to study the spreading of infectious diseases for a long time. Probably the first model is the first ordinary differential equation model for infectious diseases is due to Kamak and McDendrick, which goes back to 1927. In the paper, they define SIR to be susceptible infected recovered populations at the time t, and then they let capital M be the total population, beta gamma be the disease transmission and the recovery rates. Then they propose this simple ordinary differential equation model. Okay, here beta Si over n, this term is used to describe the interaction between susceptible and the infected people. We call this as standard mechanism, standard incidence mechanism term. Well, even though the model is very simple, it still has some nice biological implications. Okay, firstly, we can define a number called the basic reduction number R0, which is beta over gamma. Biologically, this number represents the number of cases one infected case generates on average over the infectious period. And one can show if R0 is less than 1, then the infected people will go to 0, which means the disease will go away. If R0 is greater than 1, then the disease will spread first and then go away. And the susceptible people will converge to a positive number, which means the disease will not going to infect everybody. Well, a different version of this model is the so-called SIS model. So here, the difference is when the infected people they are recovered, we assume they become susceptible again. So that's why you have this plus gamma I here. Okay. Again, for this model, you can easily see the total population still remains a constant. Okay, you add up these two equations, you can see total population should be a constant. Again, we can define the basic reproduction number to be beta over gamma. And it's easy to check the model always have a disease-free equilibrium. I will call this as DFE in the rest of the talk. And the model may have a positive equilibrium. We call the positive equilibrium as endemic equilibrium, okay, E1. Well, the endemic equilibrium E1 exists when the basic reproduction number R0 is greater than 1. Okay, and then we can show that for the model, if R0 is less than 1, then the disease-free equilibrium is globally stable. R0 greater than 1, E1 is globally stable. Okay. Again, this means R0 less than 1, disease go away. Greater than 1, will persist. Well, based on this kind of simple ordinary differential equation models, we can play around and then introduce more complicated models. Okay. Here I'm showing a so-called network model or patch model. Okay, this is proposed and studied in this SIME applied math paper. Here in this model, they assume people are living in different regions or patches. Here, omega is a collection of patch labels. Okay, the matrix L is used to describe the movement of people between the patches. Okay, L1, 2, for example, this means the movement from patch 2 to patch 1. Okay, and the diagonal elements are negative. This represents the movement out from this patch. Okay, and you, by the way, ds, di represents the movement rate of susceptible or infected people. Okay, if ds equals di equals 0, then for each patch, it follows this kind of ordinary differential equation model. Okay, so also you can see each color of L sums up to 0. This means there is no population loss during the movement of people. Okay, well, if we add up all the equations, we obtain this. Okay, this really just means the total population remains a constant. Okay, so we let M be the total population. Well, we can, okay, for this model, usually we assume L is irreducible, quasi-positive. Quasi-positive means off-diagonal entries are non-negative. Okay, well, in this paper, they actually assume the matrix is symmetric. Okay, and they let the H minus be the collection of all patch labels such that beta J less than gamma J. Okay, which means H minus is the collection of all low risk patches. Okay, and H plus is the high risk patches. Okay, by the way, beta J less than gamma J really just means the local basic reproduction number is less than 1. Okay. Okay. Well, the equilibria of this model satisfy these equations, and then the disease-free equilibrium we can check it is unique. It's given by this, and then we can define the basic reproduction number. Just follow the classical paper by Wendendrich and Waterman. So just define the matrices F and V, and then the basic reproduction number R0 is the spectral radius of F times the inverse of V. Okay. Well, if n equals 1, then R0 is just beta over gamma, which is in agreement with the ordinary differential equation model I just mentioned. Well, R0 minus 1 has the same sign as the spectral bond of this matrix. Well, this matrix actually determines, if you go back to here, it corresponds to the linearization of the model at the disease-free equilibrium. Okay. Oops. Okay, they show that R0 less than 1, the disease-free equilibrium is globally asymptotically stable. R0 greater than 1, disease-free equilibrium is unstable, and the model has a unique endemic equilibrium. Okay, so let SI be the unique endemic equilibrium, and then they show that, okay, if you send the DS to 0, then I goes to 0. Okay, what does that mean? Well, remember DS corresponds to the movement rate of susceptible people. Okay, so if you limit the movement rate of susceptible people, you are able to eliminate the disease. Okay, so that's the biological meaning of this result. Well, later on, there are some people showing if you limit the movement of infected people, well, your I doesn't convert to 0, which means you cannot eliminate the disease. Okay, if you combine these two results, you may say, okay, maybe limiting the movement of susceptible people is a better control strategy. And recently, we are able to obtain all the above results without assuming L is symmetric. Okay. And we are also able to show that R0 is decreasing in DI without assuming L is symmetric. Okay. Well, I don't know why in the original paper they propose R0 to be decreasing in DI as an open problem. You will see later on, actually, if L is symmetric, this result is easy to show. Okay, well, okay. We can also use reaction diffusion models to study the the spread of disease in space. Okay, so here this version of reaction diffusion model is actually you can think about this as the discrete version of the patch model. Okay, especially when L is symmetric. Okay, for this model, they define a basic reduction number R0 as the spectral radius of this operator, and then this R0 has a variational form. Okay, just like the variational form for principal eigenvalues. Okay, and then using this variational form, you can see R0 is decreasing in DI. Okay, well, for the patch model, we should be able to write down a similar variational form, and using that variational form, you can also see R0 is decreasing in DI. So I don't know why the authors of this paper, they didn't find this variational form, well, if the matrix L is not symmetric, then of course you don't have this kind of form. Okay, R0 is less than 1, the disease-free equilibrium is globally stable. Okay, and then R0 greater than 1, the model has a unique endemic equilibrium. Well, if then they assume beta minus gamma change sign on omega, which means there are places the domain is of high risk, and there are places of low risk. Okay, and then let the SI be the endemic equilibrium. Okay, then they are able to show that. Okay, if you limit the movement of susceptible people, you also have the I component of the converging to 0, which means, again, you can eliminate the disease by limiting the movement rate of susceptible people. Later on, the people showing if you limit the movement of infected people, you cannot cure the disease. So, again, limiting DS is a better control strategy than limiting DI. Okay, Now I'm able to present over a model. Okay, we assume people are living in different domains. Here, let omega j be the domains that the people is living in, and let omega be the collection of all domain labels. Okay, and then the model we propose is as follows. Basically, is you can think about this as a combination of the network model and the reaction diffusion model I just mentioned. Okay, so if you let the ds di be 0, okay, let the ds di be 0, then you just get the reaction diffusion model at each domain. Okay, and then, well, ds di really means the movement rate between the domains. Okay, and the dsj dij, this means the movement rate inside the domains. Okay, well, here the non-log terms are used to describe the movement between the domains. Okay, in particular, djk, this means, okay, the movement from position xk in domain omega k to position xj in domain omega j. Okay. Well, for simplicity, we just assume djk is a constant. Okay, and we let djk equals ljk over the volume of omega j, and we impose homogeneous Norman boundary conditions, and then the model we have is as follows. Is this? Well, I should mention the results I'm going to present hold for most of the results hold for the original model, but I only presenting for this simplified version. Okay. Okay. Here again, ds di are the movement rates between the patches. dsj dij are the movement rates inside the domains. Okay. Here, sj bar is the integral of sj, which means which represents the total population, total susceptible population in domain omega j. Okay. Similarly, ij bar, this means the total infected people in omega j. Again, we can add up these equations and integrate them, and then we will obtain we can show that the total population remains a constant. Okay. Okay. So we make these assumptions for the model. Okay. Firstly, we assume the initial conditions are continuous, and we denote n. Denote n be the total population, and we need the n to be positive. Okay, for the coefficients beta j, gamma j, we assume they are non-negative, hold continuous functions. Well, beta, gamma, again, they are the disease transmission and the recovery rates. Here, we do allow some components of the beta and the gamma to be 0, but we need the vector beta, the vector gamma to be not equaling 0. Okay. The matrix L, again, it models the movement between the patches. We assume is quasi-positive, irreducible, and the sum of each column is 0. Okay, we can show that the model has a unique non-negative global classical solution, and the solution is bounded So they exist M1 greater than 0, depending on initial data, such that the L infinity norm is bounded by M1. And also they exist a number independent of initial data, such that the solutions are ultimately bounded by this constant M2. Okay, well, we know that because of assumptions on L, we can use Parafluebel's theorem to get that. Okay, so the spectral bond of L is 0, which is a simple eigenvalue of L, which corresponds to a positive eigenvector alpha, and we normalize alpha such that it adds up to 1. Okay, and the L has no other eigenvalue corresponding with a non-negative eigenvector. Okay, and then the model has a unique disease-free equilibrium, E0. Okay, well, the proof of this is actually simple. Disease-free equilibrium really just means all the I components equal 0. Okay, so S will satisfy this system. Okay, well, if we integrate this equation on omega j and then using the homogeneous normal boundary conditions, we get this. Okay, we get this equal 0, which means S bar, is a eigenvector of matrix L. So that means S should be a multiple of alpha. And then because the total population is capital N, we get the S equals this. Okay. Okay. Now we define the basic reproduction number R0. Basic reproduction R0 is the number of cases one infected case generates on average over the infectious period. Measuring R0 is important, and here I'm listing R0 for some diseases, and the definition of R0 is standard for ordinary differential equation models. Okay, I'm listing here the very well-known papers on computing R0. Okay, and probably the paper by Vandendrick and Waterman is the most cited paper in the field of mathematical biology. And for partial differential equation models, Hostin has a nice definition for R0. And for reaction diffusion models, there is a paper in SIME ADS that is about computing R0 of reaction diffusion epidemic models. Okay, well, we can just follow these two papers to compute R0 for the model. So we can linearize the model at E0. Okay, so we get this. And then we let capital T be the semigroup on X induced by the solution of this. Okay. Basically, just in the previous equation, you delete beta I, so you get this. Okay, and then we let L be a linear operator defined by this. Okay, well, L is the so-called next generation operator. Well, if you are familiar with the work of these two classical papers, you can see this kind of definition is some kind of similar. Okay, and then the basic reproduction number is the spectral radius of the operator L. Okay. Well, then for the basic reproduction number, we can show that it is always positive, and R0 minus 1 has the same sign as number 1. Okay, where number 1 is the principal eigenvalue of this problem. Okay, and the number 1 is the only eigenvalue corresponding with the positive eigenvector. Moreover, number 1 tilde equals 1 over the basic reduction number is a principal eigenvalue of this problem. Okay. Well, you may wonder, okay, your R0 is defined as the spectral radius of this kind of operator. Why it is related to this eigenvalue problems? Okay. Well, actually, the intuition is very simple. Okay. Well, we can define 2 operators A, B. Okay. A, B, remember A, B are just generators of these 2. A, B are just right-hand side of these equations. Okay, B is the generator of this semigroup T. Okay, and we define C to be a multiplication operator. Okay, and then you can clearly see A equals B plus C. Okay, and the A is a positive perturbation of B, and the AB are resolvent positive operators. Okay, resolvent positive operators, they are just generators of positive semigroups. Okay, and we can show that the spectral bond of B is negative, which means we have this integral of the operator T equals negative inverse of B. Okay, this is some kind of standard from the semigroup theory. So now you can easily get L really just equals negative inverse of B times C. Okay, so L is nothing but equaling this, and using this you can just get this eigenvalue problem. Okay, get equation 4. Well, why equation 4? Why the eigenvalue of equation 4 is related to the previous to this eigenvalue problem? Well, this is by the result in this paper. Okay, the spectral bond of A, which spectral bond of A corresponds to the principal eigenvalue of this eigenvalue problem. Spectral bond of A has the same sign as R0 minus 1, okay, which is the key result in this sign applied math paper. Okay. Okay. Now I will talk about the global dynamics. Okay. R0 is a threshold value for the global dynamics. If R0 is less than 1, then the solution of the model really just converge to the disease-free equilibrium. Okay. Well, this is actually very quite obvious. Okay, if R0 is less than 1, then the principal eigenvalue here is less than 0, right? Okay, it's less than 0, and then if you go to the model, so you can see the right-hand side, right-hand side of the second equation is less than beta I minus gamma I, right? And then because the principal eigenvalue is negative, and then use a comparison principle, you just have the solution converging to 0. Okay. So at least for R0 is less than 1. Okay, it's easy to show this. Okay. Well, if R0 is greater than 1, then we can use the uniform persistence theory to show that. Okay, there exists some small number such that the solution is uniformly persistent in the sense that, okay, the solutions will be greater than some small number when time is large. Okay, so this result says the disease is not going to go away. Okay, in this situation, the model has an endemic equilibrium, okay, a positive equilibrium. Well, since the basic reproduction number you can see is an important parameter, so we will analyze R0. Okay, in the following, we will just define A over 0 to be 0 if A equals 0, and A over 0 equals infinity if A is greater than 0. Okay, then we can show that R0 is bounded below, bounded above by some expressions involving the local basic reproduction number. Okay, beta over gamma. We will call this as a local basic reproduction number. Okay, this is the basic reproduction number when you don't have movement. Okay. Okay. Well, this lemma is actually easy to show. Okay. We just need to integrate equation 4 over omega j. Okay, just go to here, go to this eigenvalue problem. Remember, lambda is 1 over R0. Okay, so we just integrate both sides. Then you kill the Laplacian, right? And then you add up, you will kill this these terms. Okay, then we just get this. Okay, and remember R1 tilde is 1 over R0, so we get R0 equals this integral. And using this expression, we can get the bounds for R0. Okay. All right. Now we analyze R0 when the matrix L is symmetric. Okay, that is the easy case. Okay. Well, again, we multiply the first equation of R0. We multiply the first equation of 4 by phi j, and then integrate over omega j. We get this. Okay. And multiply 5 by the volume of omega j, and the same sum up, we get this expression. Okay. And well, using Holder inequality, you can easily see this term is less equal to 0. Okay, so this term is less equal to 0. However, LJJ, remember LJJ is negative, right? LJJ is the diagonal, is in the diagonal matrix L. Okay, it's negative. So that means this term is going to be greater or equal to 0. Okay. Well, since the matrix L is symmetric and the spectral bond of L is 0. Okay, so that means L is actually what L is negative semi-definite. Okay, which means we have this sum less equal to 0. So again, this means this term is greater equal to 0. Okay. So combining this, we know the right-hand side of each term is greater equal to 0 on the right-hand side here. Okay. So that means we have R0 equals this. Okay. And the denominator here is going to be positive. Okay. Okay. So now we can show that. Okay, if L is symmetric, then this basic reproduction number has a variational form. Okay. Okay. Well, using this variational characterization of R0, we can see R0 is going to be monotone. Okay, going to be monotone in DI, in Dij. Okay. Okay. So using this variational formula, we are able to show this. Okay. R0 is decreasing in DI, and that R0 is strictly decreasing if and only if beta is not a multiple of gamma. And the R0 is decreasing in Dij. Okay, I remember Di is the movement, global movement rate. Dij is the local movement rate. Okay, and the R0 we can compute the limits. Okay, when the movement rates are small, R0 converge to the max. Okay, and then when R0, when the movement rates are large, R0 converge to some kind of average of the local reproduction numbers. Okay, so that means R0 is really between these two expressions. Okay. All right, now we consider the case when L is not symmetric. Okay, if L is not symmetric, of course you don't. We don't have this kind of nice variational characterization of R0. Okay, well, however, we are still able to show that R0 is decreasing in Di and is strictly decreasing in Di if beta is not a multiple of gamma. And the R0 is decreasing in Dij. And we can also compute the limits of R0 when the movement rates approach 0 or approach infinity. Okay, the only difference here is when the movement rates are large, R0 is this kind of average, or okay, it's the weighted average of local reproduction numbers. Here, alpha is the right eigenvector of L corresponding to eigenvalue 0. Okay. Well, basically, this is the main result we prove. Okay, so in the following, I will briefly talk about how we prove these results. Okay. What we did is we introduced a parameter A and let the number 1, okay, be the principal eigenvalue of this eigenvalue problem. Okay. And we will use some thing called tree cycle identity, which is from graph theory and is published in this JDE paper. Okay, to show number 1 is decreasing in Di, Dij, and strictly increasing in A. Okay, okay. We needed to associate the matrix L with a row Laplacian matrix. Okay, we call this as a row Laplacian matrix because each row sums up to 0. Okay, and then you can check because each row sums up to 0, 1, 1, 1. This is a right eigenvector corresponding with eigenvalue 0. And we let theta I be the cofactor of the i's diagonal of L. Then theta is a left eigenvector corresponding with eigenvalue 0. Okay. Well, you can think about why this is why theta is really a eigenvector. Okay. Just use the determinant of L is 0. Okay. It's not difficult to show this. Okay. So to prove the tree cycle identity, well, the tree cycle identity is actually related to something called the Kirchhoff's matrix tree theorem. Okay, so let's say you have GL be a strongly connected digraph. Okay, strongly connected really just means L is irreducible. Okay, L and let theta be just defined as above. Then we have this. Okay, theta k is the sum of the weights of t. Okay, here tk is the set of all spanning trees of the graph that are rooted at the vertex k. And the et is the arc set of t. Okay, and the wt is the product of all the weights of the tree T. Okay. Well, I'm using this example to illustrate the results. Okay. Well, the matrix here I'm putting here is actually a column Laplace matrix. Okay, each column sums up to 0, which is a little confusing because here I'm using a row Laplace matrix. Okay, here each row sums up to 0. You know, sometimes we use this version, and sometimes we use the column Laplace matrix in our papers. So well, here the example is a column Laplace matrix. Okay, then we use the alphas. Okay, the alphas they are cofactors. Okay, previously zetas they are left eigenvector. Okay, but now the alphas are the right eigenvector. Okay, well, you can easily compute alpha 1, okay, which is a cofactor. Alpha 1 is sum of 3 terms. Okay, well, alpha 1 just feels like zeta 1. Okay, alpha 1 has 3 terms, and each term corresponds to a spanning tree. Okay, for example, the red term here, A32, A12, corresponds to the spanning tree 2, 3, 1. Okay, 2, 3, 1. You see, this age from 2 to 3 is A32, and then you multiply A13, you get the weight. You get the weight of this tree. Okay, you get the weight of this tree. So you sum up the weights of these 3 trees rooted at I, you get alpha 1. Okay. Well, if you use a row Laplace matrix, the only difference here is you need to look at the trees that rooted out from vertex 1. So this means these arrows, they need to be pointing in reverse directions. Okay. Okay. The tree cycle identity that from this JDE paper is as follows. Okay. So in a lot of situations, you really need to look at a double sum like this. Okay. Okay. This tree cycle identity says, okay, your left-hand side, this double sum can be written as the right-hand side. Okay, the right-hand side is also a double sum, but this double sum is related to the cycles in the graph. Okay, here Q is the set of all spanning unicyclic digraphs. Okay, unicyclic means okay there is only one cycle in the graph. Okay, and the WQ is the weight of the graph Q, and the CQ is the directed cycle. Okay. Well, here I'm showing a unicyclic graph. Basically, without the edge from J to I, you get a tree, right? You get a tree rooted in I. And then add the edge from J to I, you get a unicyclic graph, okay, which means you only have one cycle, right? There is only one cycle. Okay. So why you have this kind of why you have this kind of identity? Well, remember theta I is what? Theta I is the sum of the weights of some trees, right? Just like this, right? Here alpha is the sum of the weights of these 3 trees. Okay. Okay. So theta should be the sum of the weights of the trees. Okay, so here, okay, WT, let's say WT is the weight of this tree, okay? And then you multiply by Aij. Remember, Aij is here, right? Aij. You multiply by Aij. Basically, it's like you multiply by the weight of the h from j to I. Okay. Then this really just equals the weight of this graph times Fij. Okay. And then you go over all the trees. You go over all the trees. You will obtain the right-hand side. Okay, and the right-hand side is related to the cycles of the trees. Okay. Okay. Using this, we are able to show number one is going to be decreasing in di. And decreasing in dij, and strictly increasing in a. Okay. Okay. Let me just briefly show you how to show number one is decreasing in di. So the idea is we look at the adjoint eigenvalue problem. Okay. Well, if we take the adjoint here, we have LKJ. Okay. The original problem is LJK, but we have LKJ here because we are looking at the adjoint. Okay. Then number one is the principal eigenvalue of 6. We know that the adjoint and the original problem, they have the same principal eigenvalue. Okay. And then differentiate this equation with respect to di. We get equation 7. And then multiply equation 6 by phi j prime, multiply 7 by phi j, and then take the difference. We get this. Okay, just manipulate these two equations. We get this. Okay, sometimes cancel out, and then we factor out phi k bar, phi j bar. We get this. And then this one is less equal to the next line. And here we use the Holder inequality. Okay. Okay, now is the place we apply this tree cycle identity. Okay, we let the A tilde be this matrix, and the L be the Laplacian matrix associated with A tilde, and then multiply A by theta j. Okay, here theta j is the cofactor of matrix L. Okay, and then sum it up and use the tree cycle identity. We get this. Okay. Okay. And then Q is the set of all spanning unicyclic graphs, and then along any directed cycle, we are able to apply. We can apply this mean inequality. Okay. To get this term to be less equal to 0. Well, and then the other sum will be equaling 0. Okay. Why is like equaling 0? This is because remember CQ is a cycle. Okay, it's a cycle. So you have like a H1 to 2, 2 to 1. Oh, sorry, H1 to 2, 2 to 3, and then 3 go back to 1. Okay, because you have a cycle. So you here we add up to 0, and previously we have this mean equality. Okay, that is exactly because all these H's, they are in a cycle. Okay, and using this lemma, we can show R0 is a monotone in DI. Okay, let me just skip this. Okay. 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 Now I'm showing some figures here. Okay. We are doing a numerical simulation with only 2 pages. Okay. 1, 2, just 2 pages, and then the transmission rates recovery rates are beta, gamma, and the matrix L is symmetric. Okay, what we are showing here is the total infected people in 2 patches. When the movement rates of the susceptible people are small. Remember previously in the introduction for the network model and the reaction diffusion model, they say, okay, you are able to control the disease by limiting the movement of susceptible people, right? Okay, so the left figure is for ds equals di equals 0, which means there is no global movement. Okay, and then in figure A, you can really see the infected people, they are going to 0. Okay, which really just confirms the results proved by the previous people. Okay, basically you can control the disease by limiting movement of susceptible people. However, if we turn on the movement between the domains, okay, let's say ds equals di equals 0.2, then as figure B shows, now you cannot eliminate the disease when you control the movement of susceptible people. Okay, the disease didn't go away. Okay, here is, we only did numerical simulations for this kind of results. We didn't look at the profiles of the positive equilibrium when the when the movement rates are small or large. So that's something we can do in the future. Okay, so my talk is based on a recent paper, which is on arXiv. Okay. Okay. Thank you for your time. Yeah.
Yeah. Thank you very much for this. There is some echo, but okay. For this interesting and inspiring presentation, and we have some time for discussion. So one of the main results of your work is that the basic reproduction number is a decreasing function of di and dij. Well, this means that the motion of infected people, in some sense, decreases the epidemic progression. Could you give us some biological or intuitive insight? Of course, it follows from the formulas for the basic reproduction number, for the eigenvalues. So for formal mathematical analysis, of course, we understand that it is like that. Yeah. But how to understand it intuitively, biologically? Why the motion of infected individuals decreases the epidemic progression?
Okay. Okay. Very good question. Yeah, very good question. So why the basic reproduction number is decreasing in DI? So that's our question. People always ask, some kind of surprise.
Sorry to repeat, but it's kind of inevitable.
Yeah. So yeah, we can firstly, it's clear from the mathematics, right? And in biology, there are also some results called the reduction principle, okay, which says movement will actually decrease the reproduction. So this is something related to the reproduction principle. Okay, reproduction principle. Okay, is something is a result in evolutionary biology. Okay, that's point 1. Okay, secondly, well, even though R0 is decreasing, that usually doesn't mean the epidemic size is decreasing. Okay, so epidemic size is not going to be monotone in DI. So yeah. Okay, so R0 is decreasing in DI. Yeah.
Yes. Okay. I think yes. Thank you. I think it's really an interesting question to continue our thinking about that, but also a little bit related question. You indicated during your presentation several times how the number of infected depend. I mean, in the endemic equilibrium, how this number depends on also DS. So, in fact, you also told us that limiting DS, if DS goes to 0, in fact, the number of infected goes to 0. So the same question, how we can understand that? Why limiting the motion of susceptible individuals decreases the number of infected people?
So, okay. Again, good question. So why limit the DS is a better control strategy than limiting
Yeah.
So,
it looks like it, well, like that on the first glance. They look symmetric. What is the difference to the motion of susceptible or the motion of infected? They propagate infection, but apparently this is not the same. There is no symmetry between the motion of susceptible and the motion of infected. Again, I'm trying to get some biological insight why it is like that.
So you can think about the low risk places as sinks. Okay, so if you allow the infected people to move, they will they will go to the sinks and then go away. One assumption in the model is beta minus gamma. They should be less than 0 at some places. So that means at least at some places you have low risk, you have local basic reproduction number less than 1. So the infected people will always move to this place and then they go away. So that's one intuition. Oh yeah.
Yeah. This is an interesting interpretation. Yes, indeed.
And I also should mention, so this kind of results are really depending on your model and depending on the mechanism you are using. So yes, I worked on the model with mass action mechanism. Let me show you. Okay, go to the model here. If we do beta Si instead of beta Si over S plus I, then we call that as mass action, right? Beta Si. This is also widely used in the models. So if we do beta Si, then you don't have similar results. Okay. So if you send the DS to 0, you cannot eliminate the disease. However, if you send a DI to 0, okay, more interesting stuff will happen. So we can show if DI goes to 0, your I component may converge to some direct delta measure. So that means the infected people may just concentrate at a single point. So
yeah, this is also very interesting.
Yeah.
Well, my last question is a little bit more mathematical, or maybe not necessarily. One of the assumptions throughout of your presentation about the matrix L, what you did is that this matrix is irreducible. Well, I understand where this assumption comes from, the mathematical development, because in the Perron-Frobenius theorem and all this related results, the matrix is irreducible. Then you have simple, the principal eigenvalue is simple, and the corresponding eigenfunction is positive, and so on. But suppose this condition is not satisfied and your matrix is reducible. Then what would you expect in this case? Like intuitively, I would think that in this case you can have really different patches, with some patches where in some sense independent patches because the matrix is reducible, in some pages or group of pages, you can have, for example, epidemic progression. In some other pages, you can have epidemic decay. So what would you expect in this case?
So I will still expect R0 to be decreasing in DI, DIJ, and I probably still expect R0 less than 1. You have, disease-free equilibrium, stable. R0 greater than 1. Well, if R0 greater than 1.
No, but if the matrix is reducible, can we expect that in fact there are different R0, different values of basic reproduction number for different blocks, for different blocks of this matrix?
Yeah, exactly. So now the equilibrium, well, then it's complicated because you have multiple equilibria. So for the equilibria, you have some patches that are positive, maybe some patches is like 0. So yeah. So that will make the analysis a little more complicated. But I think it's still doable. It's just you have more than one equilibrium. Yeah.
Okay, thank you for your answers. Let us ask also our audience, are there other questions from the audience to our speaker, please? Well, apparently I don't see other questions. So I would like to thank you again for this very interesting presentation, and I hope to have you also in the future when you have the continuation of this work. It will be really very interesting for us to listen to you and to your colleagues and to follow all these works. Thank you very much.
Thank you for having me. Yeah, it's my great pleasure. Yeah.
Thanks. Bye to everybody.